This presentation will look at multi-layered switching, or MLS, and in this we'll see how we're able to switch at layer 2 and layer 3. Normally switches operate at layer 2 using their content addressable memory. With this, the switch remembers the MAC addresses which are on each of their ports. In this case, MAC 1 and MAC 2 are on port 1, and 3 and 4 are on port 2. If the switch senses that a destination is on another network, then it forwards over the data frame to the other network, so that the whole of the switch domain is covered. This only occurs within the same VLAN. If the nodes are out with the same VLAN, then the switch will not forward them over. To show the CEM table, we have show MAC address table, and then we can look at dynamic, where dynamic means the addresses that the switch has actually learnt. We can also define other nodes to be static, and these are configured inside the switch. It learns all the MAC addresses on each of the ports. So we can see here that we have on gigabit Ethernet port G02 a dynamic learnt address. We have on FA03 another dynamic address, and so on. An important factor is the VLAN number, in that nodes inside the same VLAN can communicate directly with each other, but they cannot between different VLANs. An example of two nodes connecting to a switch within different subnets. So we can see here we have a 0.1 node and we have a 1.1 node. In this case, the node here is set up so that the default gateway is actually the Ethernet port on the switch. So its address is 0.1 and the default gateway here is 254. So when traffic needs to go out of its network, its local subnet, then it must go to the default gateway. It is now up to the router to be able to send it on to its destination. So we can see in this case the first Ethernet port is set to be 0.254, and that will provide the gateway for this node, and the second node, the Ethernet address is 1.254. so the default gateway in this case is this node. Now the two nodes can communicate with each other, because the router will take traffic from one port and then know that it needs to be forwarded to another subnet. So these two machines can now communicate even though they are on different network subnets. So the router is able to route in between, and this operates at layer 3. So what happens if we only have one network connection? Can we still communicate? And the answer is yes. This time what we do is that we create sub-interfaces, and a sub-interface is equivalent to having two interfaces. We can see here FA01.1 and .2. The default gateway for one network will be this sub-interface, and the default for the other network will be this sub-interfaces. So now we create our first sub-interface, give it the same address as we had before, and then we can encapsulate using one queue, which will allow us to trunk between VLANs. Then on the other one we create the same default gateway for it, and then we trunk for a different VLAN. So in this case this node is on VLAN 2 and this node is on VLAN 1, and the router on a stick allows us to take traffic in on one subinterface and be able to send it back on another one. This is defined as a router on a stick. A layer 2, layer 3 switch typically has this symbol here, and what we can do is that we can create two VLANs. Each VLAN will have its own default gateway. In this case, we create VLAN 1 and VLAN 2 on the switch, and then when the switch is set up so that the first VLAN has a default gateway, as we've seen before. The second VLAN is also set up with the address that we had before. Then we can create our VLAN 1 for the first Ethernet and VLAN 2 for the second. So we've now created this node within VLAN 2 and this node within VLAN 1. Then what we do is that we enable IP routing, which will allow them to be able to communicate via layer 3. They cannot communicate directly using layer 2 and must go through a layer 3 type connection. So what happens if we have multiple VLANs and multiple networks? What we must do is we must trunk in between the switches so that nodes on different switches can intercommunicate with each other. So this shows a standard distribution layer, this shows our core layer, and this shows our access layer. So typically we see layer 2 type switches at this level, layer 2, layer 3 switches at the distribution, and layer 2, layer 3 at the core level. So in this case we have a layer 3. We can have a layer 3 operation on our interface ports. So you can see here this takes us out of a layer 2 operation, and this port is now operating at a layer 3 level, and the port itself now has an IP address. In the previous examples we've seen VLANs with IP addresses. This gives us an opportunity to be able to communicate with that VLAN and with the switch, but in this case we have a layer 3 operation on our switch. The no switch port mode access will take it out of layer 3 operation and into layer 3 one, out of layer 2 and into layer 3. The IP routing command will enable IP routing and layer 3 routing on the switch. So in this case we create trunking, we allocate ports on the switch to be trunks, and this trunk will carry VLAN information across multiple switches. So in this case, if this was VLAN 1, this was VLAN 1, and this was VLAN 1, the trunk route will take the information, the traffic from VLAN 1 and encapsulate it through the trunk route to the other switch, so that VLAN 1 traffic can be sent to the VLAN 1 network, and the same again, the trunking will follow this route here and be able to be sent to nodes on VLAN 1. So typically this is what we would define as our broadcast domain. So we have a broadcast from node 1. If this node wanted to find out this node, then it would send an ARP request. The ARP would be encapsulated across this trunking route to this node and also to this node here. Nodes within VLAN 2 would not hear the ARP and would not be in the same broadcast domain. So in this case, we've allocated the second port to be our 1Q encapsulation, and the VLANs which are encapsulated in this case are VLANs 1 and VLAN 2, no other ones. This defines that it is a trunk route, and it's non-negotiable as to the protocol that it actually uses for the encapsulation. A key concept that we have is multi-layered switching. These devices work at layer 2 and layer 3. A typical entry-level MLS is the 3550 switch. Higher level one is the 4500, and a core level switch is the 6000 series switch. And these can work at layer 2, layer 3, and even go up to layer 4. The basic types that we have are either root cached or topology-based. With a root cache, we have a special switch engine and a root processor. When a first-time root is made, then it goes into the root processor. This then finds an optimal route for it, and the MLS cache is updated so that any future routing can be done through the switch engine, which makes the whole process much faster. So we have a first time hit. Once the route is determined, the optimal route is determined, then it is stored in the MLS cache, and the switch engine can easily switch it. This is typically known as route once, switch many. The other type that we have is called topology-based, or Cisco Express forwarding. In this way, we actually use the layer 3 information which we learn from the network to build a single database known as the forwarding information database. So routing information is coming in all the time, and the switch listens to this and builds up a forwarding information. With this, we can hopefully build a complete picture of the whole network and store it in our FIB. Also, as routing information is sent at continual updates, then each of these FIBs will be updated. The way that the switch works is like this. We have an incoming queue, and we have our outgoing queue, and then what we can do is that we can rewrite our data packets with the correct MAC addresses for the next hop. So inside that we have our normal CEM port, CEM table. So in this case we can actually determine all the MAC addresses, which port they're allocated to, and which VLAN they're actually on. So we can see here the CEM table has our ports and the MAC addresses and the VLANs. Along with this, we have what's called the FIB table, and this is the forwarding table. It is this table which is receiving routing information from the nodes nodes on the network. So we can do a show CIF, IP, CEF if we want to actually show this table. But basically it has a destination network. So in this case 192.168.0.0. The next hop should be this node, and the MAC address for the next hop should be this address, and then it will define the port in which it should leave. There are other elements which are processed. such as quality service and ACLs. So we can see here the CEF actually defines the network, the next hop, and then also the interface. So we have the concept of what's called adjacency tables. An adjacency table is important because it will define what the next MAC address will actually be for a packet rewrite. Because what we must do is to change the MAC address to define the next port at which we should send the data frame to. So the switch itself will rewrite the data frame to have the next hop. So we can see here that we have a show adjacency command, and the show adjacency will actually show us the IP addresses of the ports which we are next to. We can also show the detail of it, and this shows the IP address, the packets we've received, and so on. Okay, so let's see a practical example of two nodes communicating with each other. The path is from this node, node A, to node B, and we'll see how the data frame actually changes. So initially, the destination address is given as 3.1 here, which is this node. The source address is obviously 1.1. The source MAC address will be this address, and the destination MAC address will be the default gateway port. In this case, it will be this port, this MAC address. So the switch then looks up its tables, and based on routing information, it determines that the next hop should be this port here, and the exit port should be this one. So the switch will then rewrite the destination MAC address to be 1114 in this case, which will be this MAC address here. It will then change the source port, the source MAC address, to be this address, and will leave the source IP and the destination IP address the same. When it is received here, the switch will then look up and find that node B is actually on one of its ports. It will then do a rewrite to change the destination MAC address to be 116 and the source MAC address to be 115. The source and the destination IP addresses will stay the same. For level 2 type information, we can see here that when we look at the switch, we can see that it has dynamically learnt this address and also this address, where this one and this one are statically defined inside the switch. So our CEM table is basically the MAC addresses that it's learnt, the egress port, and the VLAN number associated with them. When we look at the adjacency table for this example, we can see here that the adjacency interface, in this case, is 2.2 on Fast Ethernet 0/2. And then what we see when we look at the detail, we can actually see the MAC address of the nodes in which are adjacent. The value of 7 here refers to the number of times that an FIB entry points to an adjacency entry. In this case also, the 08800 identifies that it's an IP packet. The CEF table in this case shows the forwarding table. So in this case, anything that has 192.168.3 will be sent to this IP address from that interface. So we can see here that anything that's destined for this network will always be sent out that interface, because in the routing table there is an entry for this. Anything for 2.2, that's a complete network address, will be sent to the FA0/2. So anything for the .2 address will always be sent to there, and it's marked as attached. We can also drop packets, so in this case anything for 224.0.0.0 with this 4 bits at the start will be dropped. Another concept that we have with multi-layer switches is TCAM, and with this we have an optimal evaluation of our ACLs, which allow our ACLs and quality service to be conducted in parallel with a single lookup.